Okay, so today we're going to actually get into the discussion of chaos. So I'm going to call this, so this is lecture 3. And we're going to call it, what is chaos? So most of this discussion is going to be very philosophical. We're not going to do too much math today. So let me first ask you what you think chaos is.
Something that can be predicted.
Okay. So can't be predicted. What else? Yep.
Seemingly random systems that are very dependent on initial conditions.
Seemingly random. We can put very dependent on initial conditions, but we will quantify that later. What else do we think?
It's like the nuances that's hard to calculate.
Okay. Tough to calculate. So tough to calculate what though?
The final end result.
Okay, tough to calculate, or rather predict, end result. Okay. Anything else?
It can be explained by a mathematical model.
Okay, sure. Yeah. But I mean, I guess anything in math is like that as well, right? So yes, if we have a mathematical model, then what do we mean by that? It's chaotic. So yeah, these are all good choices. So let me tell you what your homework is though for this. So you're going to write a page about any chaotic system you like. Make sure you mention what the phenomena is. So what physical system data comes from. Make sure you mention the mathematical model and say why you like it, why you think it's interesting. Don't make it more than a page and keep it like 11 to 13 point. I mean, don't make it so short that it's like half a page, but yeah.
Does that include heading?
Don't put a header there. just write one page. One typed page. That's all.
Double space or singles.
Just write enough, I guess.
Okay.
Okay, so we have an idea of what chaos is, but let's see what other people say. So if we type chaos into Google, it yields 240 million results in 0.28 seconds. So let's see what Google has to say about what chaos is. So Google says that it's complete disorder and confusion, but that is chaos as in like real life chaos, like with people, social chaos, yeah. So that does have something to do with math though. So disorder plus confusion. So the subject can be confusing at times, and there's certainly disorder. But it also gives us a more physical definition. So it says behavior so unpredictable as to pure random, so seemingly random, owing to great sensitivity to small changes in conditions. So very dependent on initial conditions. So we can put seemingly random. and sensitive dependence. So since we're going with the internet, let's see what Wikipedia has to say. So Wikipedia says something about the theory, the field itself. So it says chaos theory studies the behavior of dynamical systems that are highly sensitive to initial conditions. So again, highly sensitive to initial conditions. So sensitive dependence. So we have these sort of ideas from people that might not necessarily deal in the field of chaos, but let's see what the experts have to say about chaos. So Lorenz, and some of you have studied Lorenz in dynamical systems, so he says chaos, when the present determines the future, but the approximate present doesn't approximately determine the future. So it's deterministic, so the present does determine the future, but if you can't determine the present exactly, then you're kind of screwed with determining the future. That's basically what he means there. And he's thinking of weather systems when he says this. So Poincaré says it may happen that slight variations, and he said this in French, so this is obviously a translation of it. So he says it may happen that slight variations in the initial conditions produce very great differences in the final phenomena. A slight error in the former would make an enormous error in the latter. Prediction becomes impossible, and we have the fortuitous phenomena. So when he says this, he's most likely thinking of the three-body problem. So he actually tried to solve the three-body problem using perturbation. So he looked at basically two bodies, and the two-body problem is, of course, solved. So he looked at two bodies, and when I say bodies, I mean celestial bodies. So he looked at two big bodies and then one small one. So he could do a perturbation of the two-body problem with that extra small body. So that small body was like an epsilon m3, let's say. So he did a perturbation method, and he thought he solved it. But he actually didn't. He realized later on that it doesn't quite work like that, that small body actually throws the system off. So he realized that there was something up. He couldn't quite explain what it was, but he realized there was something there that was happening that made things weird. So these are all philosophical definitions, though. Let's think of a more mathematical definition. So Mies says this, and this will be our first definition. So he defines chaos as this: a flow. So when we think of a flow, we just think of the solution to the ODE. So that's what we think of when we say a flow. So it's basically the solution. It's a bit more complicated than that, but you can basically think of it as a solution. So a flow phi is chaotic on a compact invariant set. So we need a compact invariant set. And we're going to call this set X. So we say a flow phi on this set X that has this property of compactness and invariance. And we're saying that we want to say when phi is chaotic. So compactness in Rn, so in Euclidean space, basically means bounded and closed. Of course, if we're not in Euclidean space, it means something else. There's more a more detailed definition of compactness that deals with some machinery that you might not have seen. But in Euclidean space, it's basically closed and bounded. So you can think of a closed and bounded set. And what do you think invariance means?
That it don't change?
Okay, what doesn't change though?
Compactness?
No. So when we say invariant here, when we're saying an invariant set X, we mean that this flow, so this thing is moving around, say it's moving around on this paper, this flow will stay on the paper. It's not going to get off the paper. So that's what invariance means. So we need a compact invariant set. That's important for chaos. So it says the flow phi is chaotic on a compact invariant set X if phi is transitive and exhibits sensitive dependence on the set X. So sensitive dependence on initial conditions on the set X. So when we think of chaotic systems, we're only thinking of them being chaotic in a particular set. And that set has to have some important properties, and then phi has to have some important properties. So we'll go over what those important properties are. We don't have to worry about it now. But this is basically the definition that we're going to work with. Now, this only talks about flows. So flows are with continuous dynamical systems. So the dynamical systems that you guys are mostly used to. But we also have maps. And those who took dynamical systems have seen maps. But we're going to have the same sort of definition for maps. So we have this definition for flows, which Mies gives, but then we'll also have the same sort of stuff for maps. So we have a mathematical definition, but let's see what people in other fields have to say. So this comes from a classical mechanics book. So Taylor says that this erratic non-periodic, so let me actually write this down. So this is Taylor. This comes from classical mechanics. So he says erratic, non-periodic, so he says this erratic, non-periodic, long-term behavior. So of course it can be non-periodic for a short amount of time, but it has to be non-periodic for a long time for it to be chaotic. So this erratic, non-periodic, long-term behavior is one of the defining characteristics of chaos. The other defining characteristic is the phenomenon called sensitive to initial conditions. So sensitive dependence. So he says that. But now let's go to some more mathematical meanings, for some more mathematical definitions. So Glendinning says this. So Glendinning says, loosely speaking, a chaotic solution is aperiodic but bounded, and nearby trajectories separate rapidly in time. So it's aperiodic, bounded, and nearby trajectories separating means sensitive dependence. So I should attribute this definition to Mies. So this is Mies's definition. So Glendinning says this. He also has a formal definition. So this is the formal definition he gives. But we won't use this definition, and I'll tell you why. So he says a continuous map. So now he's talking about maps. A continuous map, f going from I to I. So f going from some set I to I is chaotic if and only if f to the n, so if we iterate this map n times, so if f of, etc. So n times. If f to the n has a horseshoe, so we don't know what a horseshoe is. So this is why we're not going to use this definition. Horseshoe for some n greater than or equal to 1. I was gonna try to bring in some dough and actually put 2 points on the dough and then create this horseshoe, but I couldn't bring in any dough. I kind of forgot about that. But that's basically what a horseshoe is like. If you take some dough and say you put 2 points on there, and then you squeeze it, you stretch it, you bend it, and then you do the same thing over and over again. So now you have dough that looks like this, but then you're going to take that, squeeze it, stretch it, bend it again. So now you have dough which has 2 of these things. So it's going to go like this, and then it's going to go around like this. And then you'll see that the 2 points are separating. They're separating very fast as well. So that's kind of what a horseshoe is like, but we won't talk about horseshoes just yet. So let's see what Robinson has to say though. So Robinson has a similar definition as Mies. So for Robinson, you can pretty much change flows to maps. Of course, there are a few things that are different because of maps, but we'll be talking about that when we deal with maps later on. But Robinson says this about defining chaos. So he says Devaney in 1989 gave an explicit definition of a chaotic invariant set in an attempt to clarify the notion of chaos. To our 2 assumptions, he adds the assumption that the periodic points are dense in Y. So his 2 assumptions are transitivity and sensitive dependence. So this guy, Devaney, also added that the periodic points are dense in an invariant set, say Y. So he says, although this last property is satisfied by uniformly hyperbolic maps like the quadratic map, it does not seem that this condition is at the heart of the idea that the system is chaotic. So we can see here that even the experts kind of disagree on this. So it's not really set in stone what the definition of chaos is. So you can kind of almost come up with your own sort of definition for chaos, but there has to be a few properties that everyone agrees on. So Strogatz mentions these properties. So Strogatz says that no definition of the term chaos is universally accepted yet, but almost everyone would agree on the 3 ingredients used in the following working definition. So this is Strogatz's definition, which is a bit of a philosophical definition, but it's a good one to write down. So this is from Strogatz. So Strogatz says that chaos is aperiodic, long-term, behavior in a deterministic system. So as someone said, it has to be a mathematical model. So mathematical models, unless you introduce probability, is a deterministic system. So it can't be a stochastic system. So in a deterministic system, that exhibits sensitive dependence on initial conditions. So that's what Strogatz says about chaos. So basically there are these varying definitions, but there are some things that everyone kind of agrees on. So we'll see that sensitive dependence comes up a lot. So that's very important to chaos. So let's see how many times it's here. So it's 1, 2, We even set it here, so there's 3, 4, 5, 6, 7 times. So sensitive dependence is important, right? But it's not everything, because you can have sensitive dependence. So say you have a dynamical system and you have 2 nearby initial conditions. So if you have 2 nearby initial conditions, you can have sensitive dependence where they just go away from each other and never come back. So sensitive dependence won't do it, because you can have systems where things blow up, right? So we can see that even on the line itself. So we can have a source, and if we have 2 nearby initial conditions, they're going to go away from each other for all time. So things can blow up. So sensitive dependence won't quite do it. So the other thing that we need is that it has to be in a certain type of set. So it has to be in a bounded set. So we're going to get that out of a few of these properties. So we'll need to have special types of sets where we can have chaos. So chaos basically happens on sets itself. So the way I think of chaos is that if you have 2 nearby initial conditions, then sometimes it will diverge from each other and then kind of go around, and it'll be far away from each other. But then you can have other 2 initial conditions where they can stay close. So it's not all of them that's expanding away, because if everything is expanding away, then it kind of blows up. But if you have some things expanding and some things not expanding, or even contracting, then you can have this seemingly random system where you can't really predict what's going on. So we'll talk about that. Basically, this is the definition that we're going to work with. So that's kind of the definition you should know. We won't do too much theory, though. So I'm going to try not to do too much theory in this course. So we won't do any proofs or anything like that, except when we do Peixoto's theorem. But I will sketch a few things. So hopefully we can understand it from sketches. So let's actually go back to Mises' definition. So let me erase everything except for Mises' definition, so we can kind of focus on that. So we go to Mises' definition, and we want to dissect what this is. So the 2 terms that we're unsure of, perhaps, is transitive and sensitive dependence. So those are the 2 terms you probably haven't seen before. Invariance, not too bad, because it just means it's going to stay on that set. It doesn't get off it. So it has to be bounded, basically. And compact just means bounded and closed. So it's going to have to be a bounded set, and the flow is going to have to stay on that set. So that's basically what those 2 mean. So those aren't too bad. Transitive and sensitive dependence are the more difficult ones. So let's first define what sensitive dependence is, and I'll give the formal definitions on the PDF notes. But here we won't do formal definitions. So sensitive dependence goes like this. And this is kind of informal. And I might even have you try to define this for me. So how do we want to define sensitive dependence then? Let's just think of how we can define it. So what do we need first for sensitive dependence?
The condition that's dependent on.
The initial conditions.
What about initial conditions then?
Very close to it.
Okay, so they're close to each other, right? So why don't we do it like this? Let's say for all epsilon, and if you guys ever take analysis, which I know most of you will, you'll see a lot of these epsilons and deltas. So for all epsilon greater than 0, let's say that there exists a y in some ball around a point x. So that's kind of how we want to think of it. So it's a weird way of thinking about this, but basically what this means is if we're on the real line and if we have a point x here, then this y is going to be within some ball of epsilon distance. But that's on a real line. We can think of it more generally on Rn. So that's why we use a ball, because in a real line, when we think of distances, we think of just the absolute value, right? But now when we're in Rn, we have to think of actual distances. So we can think of a ball. Basically, we're going to take a point x, so that's one initial condition, and then we're going to take a ball around it, and then we'll have, so this is point x, and then we'll have a point y. And that ball is of radius epsilon. So epsilon is just so we can shrink it down to any size. We can't shrink it to 0, but we can make it as small as we want. So that's what it means for things being close. So when you're asked to quantify how close, well, that depends on the person using the theorem, right? So if you want it to be as close as you want, then you need to have epsilon being a variable, and it has to work for all epsilon. So that's the idea. So if we want things that are close as we want, then we have to be able to bound it within this ball. So that's the idea for this. So for all epsilon greater than 0, there exists a y in the ball of radius epsilon around x. So that's what it means for things being close. But now what do we want to say? So we have initial conditions that are close.
So if you put that in a function, it's going to be a total different answers, a total different.
Okay, so what's the type of function that we want to put that into?
After x and
Well, how about from this definition though? So we're dissecting this definition.
you're going to put it in x, capital X?
No, so that's set, right? So that's some set. So capital X, so if this is a ball, capital X would be like some big set, right? So that's like big X there.
Would it be B?
So it's the flow, right? So we want to take the flow of both of these. We want to see what the solution does, right? So we want to take this and make it flow, and then we want to see if it separates or if it doesn't separate. So we're going to flow X, we're going to flow Y, we're going to flow it for the same amount of time, and then we're going to see how far away they are from each other. So then, let's write it like this. So we want to say such that the distance of the flow for x minus the distance for the flow of y is greater than some r for some time t. So for some time t greater than 0. So we're going to flow both of these for some time t greater than 0, and we want to see what happens to them. So the way we can think of this is like this. So we're in this set. We have 2 points that are close to each other, and then we're going to make it flow. It's going to flow like this, and then we're going to see what the distance is, and we have to be able to do this for some r. So for some fixed r. So we basically give it an r before we do this sort of thing, and then we see if there are points where this happens. So that's the idea. So the idea is you give me some distance. You give me some distance, and I will find you points where if we flow x and if we flow this point that I found, then I can be greater than that distance. So that's what sensitive dependence is. So if we have 2 points that are close to each other, It might not happen for all points. I mean, there might be some points that follow it, but it will happen. I will be able to find a point where it separates. So that's the idea of sensitive dependence. So that's that, and then now we want to do transitivity. So this doesn't mean this happens for all points. It doesn't have to happen for all points, but it does have to happen for some points. So any questions about that definition, though, before we go to transitive? So this is what it means for a flow to be transitive. So we're going to say that U and V are open sets and there exists t greater than 0 such that the flow of U intersect V does not equal the empty set. So that's basically what transitive is. Of course, I'll give you the formal definition on the notes, in the notes. But the idea is that we're going to flow some set. So let's take our big set X, and then we're going to have some little set U and some other little set V. And we want to take this and just make it flow. So we're going to flow U. So it's going to keep flowing, and something's going to happen to U. And then let's say it ends up here. So then let's say it flows into this set. So let's say this is phi t of U. So we're just going to take this, we're going to make it flow, and then we're going to see where it goes. If for some t greater than 0, it can't be infinite, it can't be infinity, it has to be some finite t greater than 0. But it doesn't tell us that it has to be less than something. So if for any t greater than 0, we get that the flow will intersect some other set that we give, whatever set we want. We can give it some set v. If it intersects this, then it's transitive. So this basically means that it's going to be wandering around. So if it didn't intersect this set, then that means that it's just going to wander back to itself at some point. But if this happens for all sets U and V, so if for all sets U and V we get this, it's going to kind of wander around this entire set X. So that's the idea. So we can't have it coming back onto itself. We need it to kind of wander everywhere, and if it does this, then we're going to get chaos. And that goes back to the seemingly random. It can't be seemingly random unless we have something that's going to be wandering around. So that's the idea. So any questions about what transitive means? So now that we know what these sort of things mean, this basically says that phi is going to be chaotic, so some flow is going to be chaotic if on some bounded set X, we get that phi is going to wander around, so the flow is going to be wandering around, and we have sensitive dependence. So if we take the flow of 2 nearby points, and we can find 2 nearby points where the flow will make it go away from each other rapidly. So that's the idea. So let me erase this. There's another little property that I want to mention. So this goes like this. So the precise theorem is going to be on the PDF notes, but let me write this down. So let me write it like this. So it's going to be a remark here, but in the notes it's going to be a theorem. So if phi is chaotic in X, and we carefully, so I will define what carefully means in the PDF notes, but here we'll just say we carefully transform it, so we're transforming phi to C in Y in some other set Y. So we're basically taking some phi in our big set X, and we're going to transform the entire thing into some other set Y. But we're going to do this transformation very carefully. So if we do this carefully, then C will also be chaotic. So this is important for us, right? So if we have something that's chaotic, we want it to still be chaotic if we transform it in a very careful manner. So obviously not all transformations will keep it chaotic, but we want it to be chaotic if we're careful about the transformation. So I'll say what careful is in the PDF notes. So any questions about chaos in general, the philosophy of chaos? So that's basically what we want to build on in this class. We're not going to do too much theory, but we want to get the idea of what it means for a system to be chaotic. So now that we're okay with systems that are chaotic, let's think of systems that aren't chaotic or can't be chaotic. So do we know of sets where systems can't be chaotic? Or can we think of sets where systems can't be chaotic?
Anything below 3-dimensional, right?
Okay. So let's think of a line then. So what sort of systems, though, below 3 dimensions? So
Not discrete.
yes, so continuous, right? So it has to be continuous systems below 3 dimensions, because with discrete systems, you can always get a system no matter how low dimension you have. Well, I mean, unless it's 0, but as long as you have some sort of dimension, you can get a system that's chaotic. Because a discrete system can bounce around, right? But a continuous system can't. You can't be having crossing trajectories in a continuous system. So let's think of a system on the line. What can happen, and maybe I should define something before this. Okay, let's think of what can happen and then I'll define it. So what can happen on a line to flows? What are the choices that we have?
It goes positive or negative, or
Okay, so we can either go right or left and flow. So let's do this. So we can have a flow where it just continues going right or left.
or it can be stationary.
When can it be stationary?
When the function is basically outputting the same result.
Okay, so yeah.
I think when you have a flow in both directions.
Okay, so what happens in those cases? So we can have something that is stationary, although that'd be kind of a trivial function though. But if we have flows in both cases, what does that mean? Okay, so we're going to have some sort of fixed point, right? We can have a stable fixed point, or we can have an unstable fixed point. Right? So these are the sort of things that can happen. So these are the only sort of things that can happen, so we can't have chaos, right? We can't even have periodic orbits there. So we can only have things going in certain directions. So that's why we can't have it in 1D. Now for 2D, it's going to be important to write down the definition of a very, very important set. So here, what do we know about this fixed point, if it's stable?
And then all surrounding points is going to come towards this.
Right. So here, where the points are headed is either to a stable fixed point or to infinity. So we can only have, in a 1D system, we can only have points headed to a stable fixed point or off to infinity. So the idea of a set that points are approaching to is very important. So we need to define a set where things are going to approach into it. We need to define a set where things go into it and then don't get out, basically. So this is how we're going to define the omega limit set. And I'll probably have a more formal definition on the PDF notes, but here, let's just write it like this. So the omega limit set of x, so omega limit set of a point x. You can have an omega limit set of a set as well. Basically, we can have flows of points, or we could also have flows of entire sets. So that's where this idea comes from. So the omega limit set of a point x is the set of, say, y, such that phi tk of x goes to y. So tk, we're basically indexing time. So we're taking a sequence of times. And it's funny that we take a sequence of times instead of the limit, but we'll see why we do that. So if we have this, so phi tk of x goes to y as tk goes to infinity. So that's how we're going to define an omega limit set. So this is basically the set of points that the flow approaches to. And we need a sequence because consider this. Let's say we have a limit cycle here. So those of you who took dynamical systems know what limit cycles are. But a limit cycle is basically just a periodic orbit where, I mean, things are going to stay there. It's not going to get away from that limit cycle. So limit cycles are just periodic orbits that are not centers. And let's say we have a flow coming in here. So now the limit cycle is going to be the omega limit set of that point x. So this is a point x, and this y, this limit cycle, has some y. So let's say there, or somewhere else. So it's going to be approaching this, these set of points, y. So now we're going to flow x, but we need to take a sequence of times, because if we don't take a sequence, so if we take a sequence, then we can get onto this limit cycle, and that's it. So we can fill in this limit cycle with our y's. If we don't take a sequence, then we have that this entire thing would be part of the omega limit set. So that's why we need to take a sequence of times. So we're basically looking at, so we'll talk about when we talk about Poincare maps, but we're basically thinking of a Poincare map there. So that's why we want to take a sequence of times. So once we have the definition of an omega limit set, then we can make some theorems and prove some things. So here, that's the omega limit set of any point on this line, right? That's going to be the sole omega limit set. So that's why you can't have chaos there. Here, the omega limit set, there is no omega limit set, because everything's going away. It's going off to infinity. Here, same thing, right? If we take a sequence of times as it goes to infinity, we're just going off to infinity. So that's why the only omega limit set is this. And we know for a system to be chaotic, we need an invariant set. So clearly the flow has to go into some invariant set. And it has to be chaotic on that invariant set. But now if the omega limit set is a fixed point, it obviously can't be chaotic. If the omega limit set is, if there isn't any, then we don't have an invariant set. So we can't have chaos in that case. So that's clear in 1D. Now let's see in 2D. So 2D, I'm going to write down the Poincare-Bendixson theorem. And this will be the only theorem I actually write down formally today. So this is Poincare-Bendixson. And this is a very important theorem. So it says let D be a simply connected subset of R2. So we're only thinking of R2. So it's going to show that we can't have chaos in R2. So we think of D as a simply connected subset of R2 and phi be a flow in D. Suppose that the forward orbit of some P in D, so some point P in D, is contained in a compact set. So again, we have this idea of compact sets. So in a compact set, and that omega of P contains no fixed points. So this P is not going to any sort of fixed point. So it contains no fixed points. Then omega of P is a periodic orbit. So basically all this is saying is that either you're going to have, if you're in 2D, either you're going to have that the omega limit set of a point P is going to be a fixed point or a connection of fixed points. So what do we know that connects fixed points? So what's a connection of two fixed points called? No. Hmm?
Saddle?
It happens when we have saddles.
Occasionally.
So if we're going from one fixed point to another in a trajectory. So heteroclinic cycles, right? So we can have heteroclinic cycles. So basically, we can have fixed points that are connected by heteroclinic cycles. So that's what it means when you're saying omega of P contains no fixed points. So if it's going into this heteroclinic cycle, then, so if omega of P is this heteroclinic cycle, then it's going into a system that has fixed points. So it can either be that. So it can either be one fixed point or multiple fixed points that are connected via a heteroclinic cycle, or it can be a periodic orbit. So those are the only choices for omega of P. So if it goes into a fixed point, so let's think of an example where it goes into a fixed point. So let's say, so this is D, and let's say in D this flow goes into a fixed point, right? So it can't be chaotic, obviously. So it's going into a fixed point, so it can't be chaotic. Now let's say that this D is going into a cycle of fixed points. So let's say these are connected like this in some way. So these are going to be connected via heteroclinic cycles. And let's say this flow is going into this cycle, right? But what happens when we go into a heteroclinic cycle? Well, it takes infinitely long to get to a fixed point. So if this is the sort of omega limit set, we're not going to ever get away from it, right? So there's no room to move around. So we can't be chaotic on that set because we've essentially gone from a 2D system basically into a 1D system, right? So you can't be chaotic in that set. Now, let's think of this. Let's say there is a fixed point, but let's say we close off the fixed point. So the set we want, so we have is contained in a compact set. So Mies doesn't name the set, but let's go ahead and name what the set is. So let's say this set is X. So let's say we have this set. There's something going on away from the set. So we can have an annulus that's compact, that's bounded, and is closed, right? So we can have an annulus. So something's happening here. We don't care what's happening, right? So the flow is doing something in here. We've already taken care of those cases, though. But let's say it's in here, right? Let's say this is P, and we're starting off here. And we don't have any fixed points in this annulus. So now where can it go? Well, it can't cross trajectories, right? So it can't go like this. So the flow can't be crossing its own trajectory. So we're going to have this. So it has to keep going around. Since it can't cross trajectories, the only way it can go is out, right? But we say that phi is completely contained in this annulus, in this compact set, right? So since phi is contained in this compact set, it has to get closer and closer to the outside portion here. But if it does that, then it's going into a periodic orbit, right? Or the periodic orbit can be further inside the set. So those are the only choices that we have, basically, in 2D. So you can either go into a fixed point, in which case it just goes into a fixed point. So you can't have chaos. Or it can go into a cycle of fixed points, in which case you're basically getting a 1D sort of motion. You're not getting 2D motion anymore. And you can't have chaos there. It doesn't have enough room to move around. It's not going to be transitive, right? So if we remember, transitive is when it wanders around. But if it's going into a cycle of fixed points, then if we take a set, that set's going to intersect itself. So it's not going to be transitive. If we go into a periodic orbit, that's not going to be transitive either. It's not wandering around there, it's just in a periodic orbit. So if we take two sets, then yes, they will intersect, but it's going to intersect itself continuously. So it's not going to be wandering around, basically. So that's the idea there. So that's why in 2D we can't have chaos. But now in 3D we can, for flows. But now with maps we can have chaos in any dimensions. But for flows we can only have chaos in 3 or more dimensions because then it has enough room to move around. So that property of the flow being transitive is important. You can have sensitive dependence in any dimensions, but you can only have something that's sensitive, that has sensitive dependence and is transitive in 3 or more dimensions for flows. So that's the idea behind chaos and what sort of systems can be chaotic. So that's it for today. Remember to hand in the homework. Just a page is fine.